Hello, welcome to my week 5 video. This week's topic is attention in transformers. We will be referencing 3 Blue 1 Brown, his video on attention in transformers, and Grant Sanderson, who actually is behind 3 Blue 1 Brown, and his speech about visualizing transformers and attention. Tokenization and embeddings are the initial step that involve breaking down the input into tokens, and representing each token is a high-dimensional vector known as an embedding. These embeddings are initially used to encode the meaning of the individual token and its position in the input sequence. The first step in a transformer is to associate each word with a high-dimensional vector. And so this is how we embed tokens in words. They also encode the position of a word. So here's a visual of tokens. They're just pieces of a sentence or whatever the input might be. And the videos from today emphasize the importance of high-dimensional vector spaces in large language models. A key concept is that the number of nearly orthogonal vectors that can be packed into a high-dimensional space grow exponentially with the number of dimensions, which means basically that large language models can store a lot more information that it might seem like they can just because of the dimensionality of embeddings and the interwebbings of dimensions. An attention mechanism in Transformer is used as a key part of large language models. We discuss how tokens and embeddings and now attention take this component and use attention mechanisms to make more sense of them contextually speaking. Attention is designed to allow the model to weigh the importance of different tokens in the input relative to each other, which is what lets the model capture contextual relationships that I just mentioned on this slide and make things a little less ambiguous. So there are 3 important vectors to consider with the attention mechanism, and those are the query, key, and value vectors. Matrix multiplication is used as a tool along with the stuff that the machine has already learned. And you take those 2 matrices, you multiply them, and that's how you generate attention values. So we start initially with the embedding of a word, which is the meaning of it without any context. Now here is a visual of that lineup. Query, key, and value vectors. From the initial embedding of a token, a sequence of vectors called keys is made, and now these keys are seen as potentially answering the queries. And the results are known as the value vector. The value vectors are added to the embedding of the second word. And here's another visual from his video. Attention scores compare query and key vectors. That's done by using the dot product. The attention scores calculated from the dot product tell us the relevance of each token to the others. So to measure how well each key matches with each query, you perform the dot product, and that tells us how likely of a pair that they might be in the context. Softmax normalization. So the process of normalizing the vector is calculated by this uh, formula here on the right. And I also provided an image that helps us see how attention gets scored, like from the calculus. way of looking at things versus the artificial intelligence formula, which I thought was interesting. And the softmax function scores these pairs from 0 to 1 based on how likely of a pair that they are going to be with each other. Value vectors are weighted by the attention weights from the previous slide that we just talked about, and these are then added together to create the weighted sum. The sum of these weights tells us the contextualized embedding of each token, and then that sum is used to determine the context, essentially. Multi-head attention. Each head has a query, key, and value matrix. So here in the image you see on the right from his video, this block actually contains 96 attention heads, and they are all working in parallel with each other. And each head has a query, a key, and a value matrix. And the, the power of multi-heads is kind of that it creates a super rich context for the machine to develop an understanding of what's going on. And this creates different contexts for the model, as well as different relationships that will tie things together. And that's all for this week. Thank you for watching.